Hello, my name is Diamantopoulos. I'm working in Braunschweig in Germany with Sasha Indren and Wolfgang Durner. And today I will present you some observations and the modeling approach we developed in Braunschweig in order to describe dynamic non-equilibrium effects. So what is dynamic non-equilibrium effects? So all started with this study published in 1967 by Top et al. In Soil Science Society. Yeah, I haven't shown. Published in Soil Science Society of America Proceedings. So what Top et al. Did, it's simple drainage experiment. They had a soil column with a packed sand, a well-assorted packed sand equipped with 3 tensiometers. They could also measure here at this point the water content with gamma ray. And they did drainage experiment for 3 different flow conditions: static equilibrium, steady state, and dynamic experiments. So Top et al. Presented their results only in one figure. This is the original figure from their paper. So here we see the pressure head from -60 to 0 and water content from 0 to 0.4. This is the retention curve obtained under static equilibrium conditions. This is the retention curve obtained under steady state conditions. We can say that both are similar. And these are the retention curves estimated under dynamic conditions. So for the same pressure head data, more water was retained by the soil column in comparison with the other two under dynamic conditions, in comparison with the other 2 cases. And this was the first study that shows that maybe they estimated the retention curve is a function of the flow condition. 7 years later, Poulos published another paper in Soil Science journal. He more or less tested the results of Top et al. However, he used another experimental setup. So he started with a long column, 55 centimeter in length, equipped with 5 tensiometers, and he made a constant flux infiltration experiment. More or less, his goal was to achieve unit gradient conditions or gravity-driven flow throughout the soil column. He obtained these conditions. He just sealed the soil column and left it rest horizontally. And now this system here has constant water content, and the tensiometer should record a stable pressure head. However, what Poulos observed, here we see suction with time, is that all tensiometers, this is the mean of all tensiometers, showed a relaxation towards a less negative pressure head value or a less suction value. And he did this for a lot of points on the retention curve. And he noticed that these effects are more pronounced in the wet range and not in the dry range. So there is a drifting of the retention curve to the left. And interestingly, he didn't notice any effect on the inhibition curve. Yeah, however, these effects, now we are measuring also in Braunschweig, soil hydraulic properties. We are trying to estimate the soil hydraulic properties. We are using multi-step outflow experiments. And these effects are here, so we are trying to deal with them because it's very important on the estimated soil hydraulic properties. I will describe very briefly the multi-step outflow experiment. We have the saturated soil column equipped with 1 or 2 tensiometers. At the bottom we have a porous plate, and under the porous plate we can apply different pressure head data, and we are recording pressure head as a boundary condition, and we are recording the evolution of the pressure head and the cumulative volume of water that leaves the soil sample. And then by inverting the Richards equation, we are estimating the soil hydraulic properties. So here we see typical results for a multi-step outflow experiment. With the red points, it's the evolution of the pressure head inside the soil column, and with the blue point is the cumulative volume of water or cumulative outflow of water. So if we look more carefully, for example, in one step, we can see here that the pressure head data, the red points, after this point here, this time point, are in equilibrium. However, the soil column continues to release water. And more specific, we can distinguish two dynamics two stages of the outflow data. We have very quick outflow data. We have a very quick outflow immediately after the applied pressure head at the lower boundary, followed by a time-dependent outflow. And of course, this data cannot be described by the Richards equation, because the Richards equation assumes that once we have equilibrium here, then the water content, or the cumulative outflow, should be also in equilibrium. Now we see here experimental results for the packed sand. Here it's the evolution of the pressure head, and here it's the cumulative outflow data. This is the fitting with the Richards equation. Yeah, some of you may say it's good, but we are saying it's not so good. So here we have equilibrium in the pressure head data. The Richards equation can describe very well this data, the pressure head data. However, it cannot describe the outflow data. And this is a systematic deviation from between the simulated and the observed data. So here are some reasons which have been proposed through the years to be responsible for this kind of effects. So briefly, entrapment of water, pore water blockage, air entrapment, dynamic contact angle, air entry effects, micro or large-scale heterogeneity can generate these effects, fluid properties, and some researchers have also proposed that maybe a combination of some of these factors are responsible for their observed dynamic non-equilibrium effects. So I'm saying that to show that it's very difficult to come up with a physically based model in order to describe these effects, because we don't know exactly what generates this type of flow. So we tried the model of Rosen's method in order to describe these effects. It needs one more parameter than the Richards equation. This is tau. It assumes that the equilibration, it decouples the pressure head and the water content, and it assumes that the equilibration of the water content is time dependent and is described by this parameter tau. Back to the data, this is the fitting with the Rosen's meta model. It's more or less the same with the Richards equation. So we have to come up with something else. So what we did is we said, okay, our soil can be distinguished into two domains. In the first domain, we have equilibrium water flow described by Richards equation. In the second domain, we have non-equilibrium water flow described by the Rosen's meta model. And if we assume that the non-equilibrium domain contributes with a factor F to the overall water flow, and that the equilibration of the pressure head between the two domains is relatively quick in comparison with the vertical water flow, then the whole model can be described by this equation here, which needs two more parameters, two additional parameters in comparison with the Richards equation, tau, which describes the equilibration of the water content to the non-equilibrium domain, and fraction, which shows the contributions of each domain to the overall water flow. Back to the data, this is the fitting with the new approach, so we can see that it can describe both data types very well. So, however, we have also as I showed you before, another occurrence of dynamic non-equilibrium effects. Here we see a new method developed by Weller et al. In order to measure hydraulic conductivity. It's more or less the same principle like in the case of Poulos experiment that I showed you before. We have a saturated soil column, we apply constant flux, we measure here the pressure head near the soil surface, and then we apply this pressure head as a lower boundary, at the lower boundary. More or less, we are forcing the system to achieve these unit gradient conditions. And we can do this also in a stepwise manner. So I will show you here results. Here we see the applied fluxes. It's a drainage experiment. The applied fluxes here. And here we see the recorded pressure by the tensiometers. And this is the fitting with the Richards equation. So the Richards equation predicts that once we have steady state in our column, we have constant water content. Here we see the evolution of the water content with time. We have constant water content. And of course, we have constant pressure head. We cannot describe this relaxation of the pressure head towards a less negative value. And it was very interesting this to try our model to see what predicts, and it looks like it can describe this also this observation. Now we have constant flux, so we can describe this pressure head overshoot. Unfortunately, we don't have any data here in order to see what's the reality here. So to conclude, there are simple observations, simple laboratory experiments show that cannot be described by the Richards equation. We developed an effective 1D model in order to describe this kind of effects. And we found very good agreement with experimental results for multi-step outflow and prescribed flux, multi-step flux experiments. So, yeah, and maybe there is a relation for these effects with what happens to the field. So, yeah, thank you.
Question or two?
Sure.
Yeah.
You thought the last chart that you showed. So when the conditions are bad, so there is no such a good fit with the model that you suggested. The same phenomena that you want to prevent.
Exactly.
When it's minus 40, look at the graph.
Yes.
Between 100 and 150, it's the same phenomena that you want to prevent. But it's not fit 100% with the observation.
Okay, the Richards equation cannot describe this relaxation at all. So
at all, no.
It's
it's better. No, it's better. Not
yeah, of course. Now it's this data series here is described with two parameters more than the Richards equation: fraction and tau. I'm not sure why should tau be stable for throughout the pressure head range. Maybe it changed. Maybe it's a function of water. However, here we just want to show that we can describe this basic non-equilibrium.
Isn't this model, this non-equilibrium model, isn't that mathematically almost identical to the dual porosity model?
Almost identically, yes.
Yes.
But not the same. For example, here.
No, I don't mean data, the model, like the.
Yeah. It's more or less the same, but there are some differences. So first of all, we have two parameters, and the mobile, I think it's 3 parameters.
3?
Yeah, I think it's
not really.
theta r.
There is,
mobile.
like
Okay, you can fix theta r.
No, I mean you have tau there, which is pretty much the same like mass transfer coefficient, right?
Yeah.
Then you divide in the mobile, so you have that f, which is pretty much, I would see that pretty similar at least.
Yeah, they are very similar. How, in the immobile, this exchange is in the effective saturation, I think.
But the domain for you is also immobile, right?
No, it's not immobile. So when fraction is 1 and we have we have full non-equilibrium conditions, then water leaves the soil column in this exponential way as predicted by Rosen-Smetten model.
Yeah.
For example, with a Philippe model, if I understood right, when we have full non-equilibrium conditions, nothing moves, so nothing comes out. There is no water movement. I think.
Okay.
The pressure difference in the immobile phase.
Excuse me?
What is the pressure in the immobile phase? I understand you include this immobile phase to account for the cumulative drainage, right? What is the pressure in the immobile phase?
We assume in our model that we have equilibration of the pressure head instantaneously between the two domains. So there is one pressure head describes our soil column, not two or more. If I understood the question right.
The pressure head is same, right?
Yes.
How the water moves? Very quickly. How the water moves from the mobile phase to the mobile phase?
there is an equilibration of the water content. So it's time dependent equilibration of the water content. So it's the assumption that we made.
It's not the pressure driven force. With the water content difference, how the water moves from the mobile to immobile? I still don't understand.
I think his problem is that you think there's one pressure, but there's still water flow.
Yes, yeah, that's what we're observing in the laboratory. Why we are observing this in the laboratory? So this also here. There is also the constant pressure head. Look only the data, not the models. Here we also is constant the pressure head, but water is still moving.
Okay, let's. Thank you so much.